Good day and welcome to the latest lecture in the series. This one is titled Energy and Steam. It's hosted by Project Solutions, who are an engineering design and project management company with offices in Teesside and Yorkshire. My name is Brian Lawson. As well as working for Project Solutions as the Technical Director, I'm the Chair of the Yorkshire region, IMechE. These lectures are supported by a number of people, not least our own Nikki Baxter, who does all the hard work in the back office for the Yorkshire region. And we're collaborating with this series with our colleagues in HQ in Birdcage Walk. So thank you to Lucy Esmond's team. We have Fiona Wong, who is giving us support on the Workcast platform today. We've previously run these lectures for the Yorkshire region and they proved very popular. And that's mainly due to excellent support offered by Spirax Sarco UK and the brilliant delivery of Dan Wells. Additionally, with this series, we also have Stephen Bishop supporting Dan. Stephen will manage any questions that are raised through the presentation. Just some logistics for your information. Questions can be asked through the lecture via the Workcast platform. The lecture will be recorded and subsequently posted on the IMechE YouTube channel. And just a shout out for the IMechE regional committees. Anybody who's connected in and wishes to get more involved with their local IMechE regional committee, you can just follow the links on the IMechE website, or alternatively track me down on LinkedIn and private message me. So without further ado, I'll hand over to Dan. It's all yours, mate.
Great. Thank you very much for that introduction, Brian. And thank you also to yourself and your colleagues at Project for facilitating and hosting this series of presentations. Thanks also to IMechE West Yorkshire and also the team at IMechE headquarters down in Birdcage Walk. The opportunity to present is really appreciated. So, as Brian quite rightly said, this is a series of CPD presentations that have been put together over the past few months. We're going through them in sequence, with the slight exception of topic number 8, steam quality. We did hope to have presented that presentation to you 2 weeks ago, but unfortunately a technical glitch meant that had to be arranged. And whilst it says the original date of the 8th of June, the correct date when that has now been rearranged for is going to be the 20th of July. And we have introduced Spirax Sarco on a number of occasions. But just to remind you, for those of you that haven't joined us on previous presentations, Spirax Sarco are a UK organisation. We are a FTSE 100 listed company. And we've got a number of different operating divisions and operating companies in different countries throughout the world. So wherever you may be based, you're never too far away from a local engineer that can offer you the support that is required. However, as far as the UK and Republic of Ireland is concerned, we're a team that's approximately 200 strong. About 50% of us are home-based, working away from our head office in Cheltenham. So again, we can support our clients in the UK, regardless of where their end-user project or their offices may be. We've previously introduced some of the resources that we have available to support end users, to support design engineers, to support facilities management companies, for example. And as you can see over towards the right-hand side of the screen, they're typically in the form of a series of online calculators and configurators, educational channels on YouTube, for example. But we can also take that one step further, because we've also got a very, very powerful suite of calculators and configurators that can be downloaded in the form of an app for your smartphone, for your Android phone or your iPhone. It's a free of charge app, and that's very, very useful because not only will it help you with the physical design of steam distribution networks. For example, sizing the steam pipes, the condensate pipes, sizing the steam traps or the control valves. It can also help you to understand the financial cost of a unit of steam. And of course, when we know the financial cost of a unit of steam, we're then also to quantify the cost savings that we can enjoy by preventing steam traps from being failed in the open position, by maximizing the amount of condensate that can be recovered, and by reducing any flash steam emissions that may otherwise be lost to atmosphere. So I'd strongly encourage you to download that app if you can. The one thing to bear in mind is it's perhaps best to download the Spirax Sarco Mexico app, as it's got far more functionality on it, and you can change the language back to English again. So we also know that the use of steam in industry is very varied. There are a whole host of different applications that typically use steam. So whenever we're talking about good working practice, steam quality, whenever we're talking about understanding how to control and distribute that steam, it's very much in mind with the requirements of the end user process. And we'll come on and we'll talk about that in a little bit more detail when we go through further CPD presentations in the series in the coming weeks. As far as today's concerned, well, the topic of today's presentation is energy and steam. And the little image on the screen is really intended to remind us that steam can be used for a variety of different applications. Typically, but not always, it's going to be for heat transfer purposes. And the image on the screen is really just meant to remind us that in that very small number of applications, it can be used for alternative sources, for example, for motive energy. So today's presentation, it is a certified presentation. As Brian mentioned, a recording will be uploaded onto the IMechE website in the coming days. And I'd really encourage you to take advantage of the fact that my colleague, Steve Bishop, is joining us on today's presentation. So if there are any questions that arise as we go through the various slides, please don't hesitate to drop them into the chat function, into the Q&A function, and we'll address those when we get to the appropriate point. So in today's presentation, we're going to review the fundamentals of steam so we can understand why it's such an attractive source of energy. And then we're going to look at how steam carries and then releases that energy before we're going to move to look at different opportunities that exist for us to improve the energy efficiency and to reduce the CO2 emissions that exist in a traditional or an existing steam system. So a slide that I've shown on a number of occasions previously, critically important, is probably the single most important slide that I would ever show on one of our presentations. And it starts off by looking at the chart over towards the far left of the screen, which we refer to as the steam tables. Over on the right hand side, the graph, that's what we refer to as the temperature enthalpy curve. But let's start off by understanding the steam tables first of all. We know that water's got a specific heat capacity of 4.19. In other words, if we want to add 1 degree of temperature to a kilogram of water, we need to add 4.19 kilojoules of energy to it. So in other words, at 0 bar gauge, we know that water boils at 100 degrees. Therefore, we need to add 419 kilojoules of energy to that water to bring it up to boiling point. We can refer to that as the enthalpy of water. We can also refer to it as the sensible heat. But that's all well and good. We don't want boiling water. We want steam. So we've got to put even more energy into that boiling water to make it fully evaporate and produce dry saturated steam. We need to put what's demonstrated in the next column, the enthalpy of evaporation, also known as the latent heat. Only when we've added the energy demonstrated in this column to the previous column are we going to get steam that exists as a gas. In other words, that water's fully evaporated. So the third column, that's the total heat energy present within the steam. In other words, it's the sensible heat together with the latent heat. So what we can see from the steam tables is by increasing the pressure, we've increased the boiling point of the water. We've therefore got to put more energy into that water to bring it up to boiling point. But we need to put less energy into the boiling water to make it evaporate to produce steam. The steam that is produced, it's going to have significantly more energy in it as we increase the working temperature. And of course, because if we've increased the pressure, we've reduced the volume that mass of steam exists at. So what you can see is, as we manipulate the pressure, all of the values in this chart change. But when steam gives up its heat energy and condenses, it's the energy that is demonstrated in this column, the enthalpy of evaporation, the latent heat. That's the energy that is imparted to the process. And what you'll notice is, as we increase the pressure of the steam, yes, there's more energy in the steam, but the useful heat energy, that latent heat, that actually reduces. And that's one of the reasons why we want to distribute steam at a high pressure, but consume it at the process at the lowest possible pressure. So moving across to the temperature enthalpy curve, this really demonstrates the journey that water takes as it evaporates to produce steam. And we're using the example of 0 bar gauge here, where we know water boils at 100 degrees. So if we move the line across horizontally, you can see it's only when we've added that 419 kilojoules of sensible heat that water is going to boil, and that's when we can say the evaporation process starts. Steam starts to be produced. But it's only when we've added the full enthalpy of evaporation or latent heat that we can say the evaporation process will have ended, and we've now got a mass of steam that is fully dry and fully saturated. So if we're not on top of how we're generating steam in the boiler house, for example, if we've got less than optimum boiler controls, if we've got fuel that's slightly contaminated, it's highly likely that we won't be putting the full latent heat energy into that boiling water. In other words, the steam will exist slightly to the left of what we call the dry saturated steam line. So that word dry saturated is critically important. Dry, well, it means there's no moisture entrained within it. Saturated, it means it's saturated with energy. Cannot contain any more energy than 2,676 kilojoules in the example of generating steam at 0 bar gauge. So problems caused by wet steam. First of all, wet steam is far more likely to give up its energy to the distribution pipework and condense. So we can start off by generating 10,000 kilograms per hour of steam, but we could be losing 500 kilograms per hour to the pipework, meaning we get a reduced mass of steam finding its way to all of those processes. It's an inefficiency. That condensate, it needs to be removed. So the wetter the steam, the more condensate, the more steam traps we need to engineer and maintain. If we've got condensate that exists in the distribution pipework, we're more at risk of corroding pipework and other ancillaries. We're more at risk of erosion, and we're more at risk of water hammer, all of which are mechanical maintenance issues we'll need to contend with. But from an energy perspective, remember, the more condensate is given up to the distribution pipework, the greater the inefficiency. But because of the condensate that languishes in the distribution pipework, it's inevitable that that steam that finds its way to the process is going to be wetter. And the wetter the steam, the less energy there is contained within the steam. So as far as the process is concerned, for one, we get less energy being distributed to the steam, and we get a reduced mass of steam being distributed to the process, all as a result of us generating and distributing wet steam. So it's important to bear in mind that the steam tables, all the information that's shown on the steam tables here, it is based on the understanding that the steam is in a very, very dry condition. Anything less than perfectly dry steam will result in a greater condensate load and less energy being present for the process. So as you can see, if we increase the pressure of the steam, we've reduced the volume. We've increased the total heat in the steam, but there's less useful heat. And that's why in previous weeks we mentioned the benefits of reducing the steam pressure ahead of the process. It means that we're able to utilize that latent heat energy more readily and more efficiently. Now, the other things that the steam tables tell us that we've discussed in previous weeks, it's that pressure to temperature relationship. If we know the pressure of the steam, we know the boiling point of the water, and therefore we know the temperature of the steam. For example, if we're generating steam at 10 bar gauge, the boiling point of the water would be 184 degrees, and therefore the temperature of the steam is 184 degrees. But if we only want to use steam at a heat exchanger that requires to have a temperature of, say, 130, 132 degrees, it tells us that we can achieve that simply by reducing the pressure. So for that reason, we only actually need a two-port valve to control the release of energy from the steam onto the process, onto the heat exchanger. Whereas if you compare that with a water-to-water heat exchanger, well, we need a three-port valve, and we'd need that for two different reasons. First of all, steam gives up its heat energy by condensing. So the heat exchanger will only call for and condense the amount of heat that the process requires and no more. But because of that pressure temperature relationship, it also means that it's even easier to control. For example, a water to water system, well, we know that the water needs to be pumped across the heat exchanger. And we also know that we need to divert away any energy that isn't required by the process, hence the third port and that little circulating pump, neither of which are required on a steam to water heat exchange system. And we also need to remember that pressure to volume relationship that we've spoken about. We know if we've got a kilogram of steam existing at 10 bar gauge, it occupies a very, very small volume. Whereas if we've reduced the pressure of that steam, say downstream of a pressure reducing valve, then because there's nowhere near as much compression on that steam, it's going to exist at a much, much greater volume. And in the example of looking at a kilogram of steam at 0 bar gauge, we can see that its volume is approximately 1.673 cubic meters. So it really emphasizes the benefit of distributing steam at the highest possible pressure. And in the vast majority of building service applications, we're typically talking about a high pressure of 10, maybe even 12 bar gauge. The reason being is the rate at which we can really compress that steam volume is going to start to really plateau off, and we're not going to see too many cost savings by being able to reduce the infrastructure much greater. But the little graphic really helps to emphasize the fact that if we can increase the working pressure of the steam boiler, then we can distribute the steam at a high pressure in a very small pipe diameter. So, of course, there's going to be a significant cost saving on the infrastructure there, but there's another cost that is often overlooked, and that's if we've increased the working pressure of the steam, increased the distribution pressure, reduced its volume, and therefore reduced the infrastructure size. We've also reduced the space or the area that the steam can give up its heat energy and condense against. So that means we're reducing the radiation loss. We've got less condensate to remove. So we've got a greater efficiency with fewer steam traps to install. And the steam is going to be far, far drier, meaning we've got fewer mechanical issues and meaning there's more heat energy present in the steam to satisfy the process. And just taking that one step further with regards to understanding the benefits of distributing steam as a gas and as a compressible gas at that. Well, if we compare the distribution network for steam to low temperature hot water, well, we've already mentioned in previous presentations, steam has got approximately 50 times the latent heat, the useful heat energy present in it, than a low temperature hot water system that could have been designed to give up 11 degrees of heat at the process, 50 times more energy. So of course we need to generate and then distribute 50 times less to get the same heating effect. The other thing is steam's a gas, it's compressible. So of course we can distribute the heat energy in the steam in a much smaller pipe diameter when compared to a low temperature hot water system. We also know with a liquid based system, we've got a single phase liquid going out and we've got a single phase liquid coming back from the process. But of course, when we compare that with a steam based system, well, we know steam gives up its heat energy by condensing. That phase change from a gas to a liquid condensate means we've got the steam going out in a very small infrastructure, but we've got the condensate coming back in an even smaller infrastructure. Now, we're not making the claim that that means that the infrastructure is going to be cheaper, more economical. In some cases, it may be, but we're not making that claim. We're making the claim that by reducing the infrastructure size, we can have significant benefits that we can enjoy because we're distributing it in smaller plant room voids, smaller culverts, and so forth. And of course, that is inevitably going to result in a benefit to the steam using site. But one area that is often overlooked is the distribution costs with steam. So we know that steam as a gas, well, it's not pumped. The steam is going to move from the boiler house to the various processes around site under its own motive energy. It's a gas. It flows in accordance with the pressure drop. But we know that with a liquid-based system, if we're comparing steam to water, we do need to pump that water. And the thing to bear in mind is whenever engineers are benchmarking the benefits of water against steam, quite often they quite rightly identify that because we're generating steam at higher pressures and therefore at higher temperatures, we need to consume more gas. Of course we do. We recognize that. But the thing to bear in mind is the cost of pumping that liquid energy, that low temperature hot water, the pumping costs can quite often outweigh the benefits in generating that low temperature hot water with a lower gas consumption. So just to put that in further financial terms, we've got a chart here that is comparing steam to low temperature hot water with a 20-degree delta T, 60 to 80, and the same delta T, but at typically higher conditions, 70 to 90. As you can see, straight away, we've recognized that the cost of gas is going to be significantly greater to produce steam than it is to produce hot water in each of the examples. But when we add in the electrical requirements to satisfy those circulating pumps, you can see that the cost benefits of producing water are significantly diminished. And in fact, it's more attractive to compare steam. Now, there's a very small pumping requirement demonstrated there, 0.7 kilowatt, because it's inevitable that we require an electrical pump to bring the water from the hot well into the boiler itself, maybe even a circulating pump on the hot well just for anti-stratification purposes. So we have factored those small pumping costs in there. And another point that makes steam a very interesting source of heat energy is it's got a very high heat transfer coefficient. That's often referred to as a U value that you may remember from one of those thermodynamic equations that we looked at in previous weeks. It's the speed of heat transfer, the speed at which the energy in the steam passes across the thermal barrier into the process. And you can see that if we're using steam, the speed of heat transfer is about 3 times greater than that of water. So that basically means if we've got a high U value, it therefore means that we need a smaller heat transfer surface area compared to a water-to-water heat exchanger. And Because most plate heat exchangers that are used on steam systems are gasketed as opposed to welded or brazed, it means that we can further manipulate that U value by taking apart the plate pack periodically for cleaning or descaling. It means we can help to keep that heat transfer operating at a very, very rapid time. It also means we can future-proof, because if we've got a gasketed plate pack, it means we can increase the surface area by adding the number of individual plates or removing them to ensure that the process is correctly sized and correctly optimized. But ultimately, if we've got a high speed of heat transfer and a small area, heat transfer surface area, it means we require a smaller heat exchanger, we've got smaller plant room space, and we've got fewer radiating losses. We've got a greater efficiency. As we've mentioned, one of the most important things to bear in mind is we want to ensure that the steam is kept as dry as we possibly can and free of air and other non-condensable gases. And BSEN 285, it is a standard that we can use to benchmark the condition or the quality of the steam. We'll come on and speak about this in a little bit more detail in coming weeks. It is a standard that is widely referenced by applications that may use steam for critical purposes, such as hospitals, pharmaceutical, food and beverage, fine chemical applications. But when we're talking about using steam for general purpose, general heat transfer purposes, we really just want to ensure that we're keeping the steam as dry as we possibly can, for the simple reason that the drier the steam is, the more energy is present within it. But we also need to give thought to the air and the other non-condensable gases. If we've got a significant mass of air and other non-condensables entrained within that steam, then we know that there's going to be a barrier to heat exchange. So let's have a look what that actually looks like on the steam tables. As we've mentioned previously, the steam tables that are demonstrated up in the top left-hand side of the screen, they are based on the understanding that that steam is perfectly dry and free of air and other non-condensable gases. And for reasons we've gone through previously, it's nigh on impossible to guarantee that that steam will arrive at the process 100% dry. But if we use the example of really not being on top of how we're controlling the steam in the boil house, if we're not observing good working practice with how we distribute the steam, then it's inevitable that we could have an excess of moisture or a very poor dryness fraction. And in the bottom of the two curves, you can see the example of us having a dryness fraction of 50%. In other words, the steam's 50% dry, 50% wet. That means there's 50% of the useful energy contained within the steam. So of course, if that is the case, and we're supplying significantly wet steam to a process where the heat exchanger has been sized on the assumption that the steam is 100% dry, then essentially the heat exchanger is undersized. It means it's going to take longer and longer for us to get the required heat energy into the process. So the process time can extend and extend, or it could well be that we just fail to hit the required process temperature altogether. And if we take that one step further and add in the fact that we may have air and other non-condensable gases entrained within that steam, then you can appreciate it makes it increasingly difficult to ensure that we're reaching the required process design conditions. So in previous weeks, we've spoken about how it's the steam traps that are perhaps one of the single most important components on the steam distribution loop. If the steam traps aren't sized and selected correctly, then they're highly unlikely to be working efficiently, and sooner or later they are going to fail and result in a significant loss of energy. We remember there's no such thing as a one-size-fits-all universal steam trap, but we also appreciate that if we know a few key variables, if that steam trap were to be left failed in the open position, then we would have a significant mass of steam venting away to atmosphere, a huge inefficiency. Now, every steam trap size has got a similar sized, or every steam trap type has got a similar sized orifice, regardless of its operating principle, regardless of its configuration. So if we know the size of the steam trap, and if we know the pressure that we're distributing that steam at, together with a few other key variables, such as the operational number of hours per year of the steam boiler, then we're able to determine how much energy is being lost for every year whilst that steam trap is left in the open position. It can be a significant loss of energy. So we know that a lot of industries at the moment are under pressure to address sustainability challenges, and ensuring that the steam trap population is routinely audited, or that we've got measures in place to identify when a steam trap has been left in the failed position. This can have a significant impact and a very rapid payback for the benefit of a steam using site. Other ways that we can optimize the process are by examining what type of heat exchanger do we have. Have we got a shell and tube heat exchanger, or have we got a plate heat exchanger? Now, one of the benefits of moving away from a shell and tube heat exchanger to a plate heat exchanger is, well, even though the heat transfer surface area in the plate heat exchanger, even though the thermal barrier is greater, the actual size of the solution is significantly smaller. So a key benefit there, smaller plant room space. Another key benefit is, well, we're not holding up as much water in the plate heat exchanger as we are in the shell and tube heat exchanger. So we can reduce those standing losses significantly. And we also know if we've got a greater heat transfer surface area and a greater heat transfer coefficient, then this is one of the reasons why we can generate processed water, hot water from steam instantly and on demand. And it helps us to really address the challenges that are often seen by having an oversized shell and tube heat exchanger. So we can very, very easily optimize a process that may have a significant demand for hot water simply by addressing the type of heat exchanger that is used in the plant room. Other ways that we can help to optimize and improve the energy efficiency of an existing steam network are by having a look at the condensate side, the condensate network. So we know condensate exists wherever steam gives up its heat energy. That can be in the distribution pipework, or it can be at the process. The important thing to bear in mind is that we need to recognize the value of that condensate and get it back to the boiler house. The reason being, well, it comes back to the steam tables again. If we look at the steam tables, if we know the pressure and the temperature that that condensate exists at, we know how much heat energy is present within it. It's the sensible heat. And typically that sensible heat, the byproduct of steam when it's given up its heat energy, that sensible heat that's left behind in the condensate, typically is going to amount to 20 to 25% of the total heat energy in the steam. But not only that, that condensate is still water. So the more condensate we can recover, the less raw water we need to consume. So condensate does have a value at the boiler house. It just doesn't have a value at the process. And I just want to reiterate that quite a lot of steam using sites fail to recover the amount of condensate that they could potentially do so for a failure to appreciate what condensate is and how they need to handle it correctly. So if we look at a typical steam using process, we know that when steam gives up its heat energy, it condenses. It changes state from a gas to a liquid. So if the process is calling for a mass of 100 kilograms per hour of steam at 7 bar gauge, 170 degrees, well, we know the condensate is going to exist at 7-bar gauge, 170 degrees, and at the same mass, 100 kilograms per hour. But the problem we have is understanding that the behavior of the condensate when it moves across the steam trap means that there is going to be a pressure drop. We need to have that pressure drop. We need a good motive energy upstream of the steam trap so the steam can push the condensate away so it can travel back to the boiler house under its own motive energy. But the problem is, if we've got a significant fall in pressure downstream of the steam trap, by referring to the steam tables, we understand that, for example, a fall in pressure from 7-bar gauge to 0-bar gauge means that the sensible heat has got to fall from 721 kilojoules to 419 kilojoules. So how can that condensate give up that energy in such a small distance? The answer, well, a certain mass or a certain percentage of that liquid condensate is going to change state back to steam again. We call that flash steam. But what you may recall from that slide towards the start of today's presentation was that pressure volume relationship. Flash steam that exists at 0-bar gauge is going to occupy a volume of approximately 1.673 cubic meters. In other words, we need to size the pipework downstream of the steam trap to allow for that huge and rapid expansion very, very quickly. And that can be quite costly to do because we could be bringing that condensate infrastructure a considerable run back to the boiler house. So inevitably, at some point, that flash steam will find its way being vented away to atmosphere to allow the condensate to fall back to a single phase liquid again. So whenever we're talking about increasing or maximizing the amount of condensate we can bring back to the boiler house, we need to talk about the flash steam. We need to talk about either reducing the amount of flash steam that is going to be produced, or we need to look at reusing or recovering that flash steam to use that energy in some other way. There's just as much flash energy in a unit of flash steam as there is in a unit of plant steam. And also, if that flash steam is vented away to atmosphere, well, the problem is that we're missing the opportunity to recover that liquid condensate. The flash steam and therefore the condensate goes into the atmosphere. So whenever we're talking about recovering condensate, or whenever we're talking about understanding the financial benefits of engineering a solution to minimize flash steam and maximize condensate recovery, we need to know the condensate load. We need to have an understanding for the amount of energy that's present in that condensate. We need to know how much our raw water costs, what our effluent costs are. We need to have an understanding of what our chemical costs are. And it's only then that we can start to appreciate the benefit of engineering a solution that will increase the rate of condensate return and minimize the amount of flash that is expelled to atmosphere. But we also know that certain processes are knowingly dumping the condensate to waste. And that could be through fear of the condensate becoming contaminated with oils, fats, acids. Because if we brought that contamination back to the boiler, then that could be quite a costly failure for the boiler itself. But it could also mean that we're potentially cross-contaminating other processes. We could have contaminated steam going out to other areas of site. So quite often, sites are knowingly dumping that condensate to waste. But there's an opportunity here to recover it when it is in an excellent condition. The reason being, if we can move towards a turbidity or a conductivity probe that could sit a run of pipework ahead of a diverting valve, well, it can dump contaminated condensate to waste when it's not in a condition to be reused. But when it is in a good condition, we can make use of that hot water by bringing it back to the boiler house. And even if that condensate is being dumped to waste, then maybe it can be put to waste across a very simple heat recovery solution. So contamination control devices, they can either be mounted in line, or for larger solutions, they can be skid mounted. It basically comes down to recognizing the value that that condensate has as hot water. Other ways that we can optimize in an existing steam using system is by looking at the blowdown. Now, we've spoken previously about what the blowdown controls are, what they do. And that really comes down to the understanding that the chemicals and minerals that are present in the water, together with the chemicals and minerals that we add to the raw water, are going to behave in two different ways. And the analogy that I usually use is it's like having a cup of tea at home. And you put a spoon of sugar in your tea, it dissolves. You put a spoon of sand in your tea, and it falls to the bottom of the cup. And over time, if you put in more and more sugar and more sand into the tea, a number of different things are going to happen. First of all, the sand is going to start occupying quite a lot of the space within the cup. And secondly, the more sugar you put in the tea, then that tea is going to get saturated with sugar and it's going to start to get very, very frothy. So let's move that analogy across to a typical steam using boiler. The chemicals and minerals that solidify and fall to the bottom of the boiler, they're going to need removing. And we do that by using a bottom blowdown valve. And the bottom blowdown valve, well, if we open that valve for a couple of seconds, once a shift, every 8 hours, then the pressure that the steam boiler is working at will blast that sediment away across the valve to a much lower pressure. And then we just close the valve, and the falling water level is recognized by the level control probes, and that calls for that water to be replaced by a lower concentration of water that comes from the feed tank. The point is, we need to recognize exactly how much blowdown we need to be performing. Because if we perform too little blowdown, we're not getting rid of all of the sediment. If we perform too much blowdown, then it's a significant waste of energy. That hot water that's going to waste needs to be replaced. It will be replaced with cold water, and we'll need to add more energy to it to bring it up to the point where we can start producing steam again. So we can either perform that bottom blowdown manually, but it's far, far better if we can move towards a system whereby we've got a timer on an actuator that is going to open for the prescribed number of seconds. And if we know the pressure of the boiler and the number of seconds that the valve is open for, we can determine exactly how much hot water we're dumping to waste. We can keep those inefficiencies to a very, very low point. And then we've got what we refer to as the TDS, or total dissolved solids. So that comes back to the analogy of the sugar that I was speaking about. As we start to evaporate the water, then the chemicals that are present within the water in the boiler, they become more and more concentrated. And if they're left unchecked, if it were to reach a dangerously high level of concentration, we'd get a lot of foaming present in the boiler. And that can be an indication that there's a lot of a buildup of scale and insulation on the heat transfer surface areas. It can also make it very difficult for the level control probes to determine the true water level. But as we get a fluctuation in pressure, we can draw out that foam into the distribution pipework. It's going to be very wet and sticky, and it can also result in a little bit of erosion to sensitive areas. So typically we address the TDS by taking a sample from the side of the boiler. We'll put conductivity probes across it. If and when it reaches a high conductivity, that's an indication that we've got a high total dissolved solid content in parts per million. We dump a certain mass of that high TDS boiler water to waste, and the level control probes then call for the same mass of cold water for us to bring the boiler up to the correct operating level again. But again, if we blow down too much, then we've got a significant inefficiency from an energy perspective. If we blow down too little, we're at risk that we're going to get steam contamination and very wet, sticky steam with very little energy in it. So we want to recognize the benefits of moving away from a manual TDS system to an automated TDS system. And that's typically operated by having a conductivity probe that sits in line ahead of a modulating valve. So it can be constantly drip feeding the exact prescribed mass of hot water to waste. But we know that the bottom blowdown, it's got a lot of sediment in it, so it does need to go to waste. Whereas the TDS, the solids are dissolved. So that hot water that goes to waste is in an excellent condition for doing so once it's gone across a simple heat exchanger. So a typical TDS heat recovery solution that can enjoy a very, very attractive payback that is very, very easy for us to measure for our clients. We also know that moving away from a traditional atmospheric hot well towards a pressurized deaerator is also going to have a number of other benefits. If we're elevating the pressure that the water is held at, we can elevate the temperature from 85 degrees in a typical atmospheric feed tank to around 105 degrees. So of course, we can generate steam far, far more rapidly whenever there's a demand. There's going to be less thermal stress placed on the boiler if we're putting hot water into it rather than slightly colder water. But it also means we've got a good head start and we need to consume far, far less fuel to raise steam again. But because of the pressure, then we've purged off a lot of the non-condensable gases and a lot of the oxygen, which typically causes corrosion. And because of that, we need to add fewer chemicals to the feed water. So there's a cost saving there. But because we're adding fewer chemicals to the feed water, we need to perform less of that blowdown. And also it means that because we're holding that water under pressure, we can recover more of the flash steam. It doesn't necessarily need to be vented away to atmosphere. So a pressurized deaerator can it can address a number of challenges that large steam using sites have. And this really is increasing in popularity, especially in the food, beverage, pharmaceutical sectors that require a massive steam to be supplied to the process at a consistently better condition than plant steam. But we also know that, coming back to those flash steam losses, we know that flash steam venting away to atmosphere is inevitable. The little video over towards the right hand side of the screen, that kind of flash steam vent, it is very easy to identify, especially on a cold day. And not only are we likely to have flash steam vented away, it is likely that any failed open steam traps will also be vented away to atmosphere from the same point. So we want to keep an eye on our flash steam vents. And if we see a significant amount of flash steam being vented away periodically, then it tells us there's an opportunity to do something about it. Because, as we've mentioned previously, there's just as much energy in a kilogram of flash steam as there is in a kilogram of plant steam. Ways that we can recover that flash steam, it can be something along the lines of a dedicated flash recovery energy management device. And typically that will be used to add energy to another heat sink. For example, we could use it to preheat the boiler feed water. So the water that was leaving the feed tank could take on an excess of energy before it was finding its way injected back into the boiler again. The key thing is that we see flash steam as having a value and not simply being a byproduct that we need to expel to atmosphere to protect against that expansion. Other things that we need to think about, it's the measurement of the amount of steam that is being distributed and condensed. And just as there's no such thing as a universal steam trap, there really is no such thing as a universal steam meter. There are different types of steam meter that we may want to give consideration to for different applications. But the important things to look out for whenever we're sizing or selecting a steam meter are, first of all, the turn down. And that's the difference between the highest and the lowest flow rates that it'd ever need to read. The next thing is the accuracy, and that's the ability of the meter to read a true and correct value. And then we've also got the repeatability. And the repeatability is interesting because that's the ability of the meter to read the same reading time and time again. Might not necessarily be an accurate reading, but it's the same reading. So with regards to accuracy, it's important to understand that different manufacturers, they'll quote accuracy in different ways, and this can be really misleading. So if we look at FSD, that's full scale deflection. Let's say if we had a flow meter that was passing 1,000 kilograms per hour of steam at a 100% capacity, and if it was quoted as having a 3% full scale deflection accuracy, then that could mean that there was 30 kilograms per hour of steam that was not being read by the meter. But let's say the process demand for steam could have fallen from 1,000 to just 100 kilograms per hour. Then that means that that very same meter, it could still be failing to measure 30 kilograms per hour of steam. So what was a 3% inaccuracy at a full capacity, it then becomes a 30% inaccuracy at the lower capacity. So it's far, far better to have an understanding of what's called an indicated flow accuracy, because that means that that percentage that's quoted is going to remain exactly the same regardless of whether we're looking at the higher turn down or the lower turn down. So certain applications, especially those where steam is being used for heating or domestic hot water in a public building, they're going to require a flow meter to be fitted. So whenever we're performing remedial works, for example, if we're upgrading or if we're stripping down a heat exchanger, then CIBSE Part L states that if we're going to be servicing an elderly shell and tube heat exchanger or a calorifier, then we should be fitting a steam meter in order to remain compliant. But it's still good working practice to fit a steam meter. Just for good working practice purposes, we want to ensure that we've got a steam meter fit ahead of the process and in the boiler house. So that could be for budgetary purposes. It could be so we're monitoring any distribution losses between the boiler house and the process, or it could be for fault finding. For example, if a process is calling for more and more steam over a short period of time, it could well be it's down to the fact that the heat exchanger is starting to scale up. But the thing we need to bear in mind is that as with a steam trap, we need to install a steam meter with a number of different ancillaries to ensure that it's going to operate correctly, it's going to take a true and accurate reading, and it's not going to fail. So we want to remove the moisture and the debris, the particulate, so it doesn't create erosion problems. We want to vent the air away. We want to remove the condensate. We want to have a correct run of pipework upstream and downstream to maintain linear flow. We want to install a check valve so that we don't have a massive condensate being pulled back across the steam meter if we get fluctuating pressures on the steam side. But we can also take the steam meters one step further. For example, if we've got a number of different meters in the boiler house that are sending a signal to a boiler house energy monitor, then we can get a true understanding of the actual steam distribution efficiency. Let's say we've got a raw water makeup meter. Let's say we've got a fuel meter. We could have a meter between the feed tank and the boiler, and we could be metering the steam that's going out to the various processes. Let's say over a period of months, the amount of steam that's being produced and the amount of water that's being supplied from the feed tank to the boiler, that could have remained relatively stable. But we could have been calling for more and more raw water and calling for more fuel. And by taking a reading of the boiler house energy monitor, we can understand the reasons why that is. For example, if we're not recovering anywhere near as much condensate as we were previously, if we've got a steam trap that's failed in the open position, or if we were starting to vent a lot of flash steam away, well, we need to replace that with more raw water. And we then need to bring that water up to the point where we can generate steam again. So it gives us a good understanding not only of where that inefficiency exists, but it tells us the burden of that inefficiency in financial terms. But we also know that there are other areas of the site that could benefit from an understanding with regards to where an inefficiency may lie and what a likely payback is going to be. So many of our engineers, they've got very sophisticated software on their device, on their tablets, and by asking a few very, very basic questions, then we can determine the overall health and efficiency of the wider steam and condensate loop, and we can start to identify where payback opportunities may exist. For example, moving away from those manual blowdown controls to install automatic timed blowdown controls. Will there be a benefit to fit in an economizer on the flue? How much condensate is being returned? How much flash steam is being vented away? Is there an opportunity for heat recovery from the TDS blowdown and so forth? It means that we can really start to get an understanding with regards to the projects that will allow an enhanced operation, a reduced cost of fuel, and a reduction in carbon emissions within the boiler house. Other things that are growing in popularity at the moment, we know that a lot of steam using sites are moving towards CHP systems for obvious reasons. We know what the benefits are. They're outlined on the graphic that we can see on the slide above. But we also know that we can improve upon a well-designed and a well-balanced traditional CHP system to incorporate that into a modern steam system, what we refer to as a CSHP, or a combined steam, heat and power distribution network. And I just want to leave you on one last thought, and that is, traditionally, we've always considered that steam is to be generated utilizing fossil fuels. And we also know that the flash steam principle that we spoke about, that's where steam can be generated simply by reducing the pressure of a high temperature liquid such as condensate. It means that we can now generate steam by using renewables. It could be heat pumps, it could be aerothermal, it could be solar panels, or it could come from the grid. By using power to charge a pressurized vat of hot water, then we can now produce steam to satisfy a process simply by reducing the pressure, producing that flash steam, and then distributing it to the process. And this is a solution that we're going to come on and discuss in a little bit more detail when we speak again in 2 weeks' time on the topic of steam, the future. So again, I'd like to thank you for your attention during today's presentation. Much appreciated. I look forward to presenting to you again in 2 weeks' time on the topic of steam, the future. If there are any questions, please don't hesitate to put them into the chat function. I'll ask Steve to open up the microphone now and read out any questions there may be.
Hi, Dan. Good afternoon, everybody. Yeah, thank you very much, Dan, for another excellent presentation there. Lots and lots of information and a really good insight, actually, into some of the areas that we can look at with regard to an existing steam system and designing in further energy efficiency. So really, really good, really useful information there. There are a couple of questions. So if I could read those out to you, if you wouldn't mind.
Yeah, please do.
So the first one is a question from Anthony. And he's asking, do you also need pumps for condensate return?
Difficult question to answer. If you can imagine a hospital, a tower block hospital. If we've got a plant room on the 10th floor, then the condensate as a liquid could potentially return back to the boiler house under gravity. However, if we've got a distribution network that is quite vast, spread out horizontally, for example, then it may well be, if we're condensing the steam at a low pressure, let's say we're condensing the steam at 1 bar gauge, 120 degrees, then there isn't going to be enough motive energy in the upstream of the steam trap to push the condensate a considerable distance. Under circumstances such as that, we may need to add some motive energy to that steam. Now, that could mean pumping it in the traditional sense, using electrical circulating pumps, at which point we've got to allow for the condensate to cool down to 100 degrees or less and vent that flash steam away. Or we could use what's referred to as a mechanical float pump, or an MFP. And that basically allows us to we basically borrow the motive energy from the steam distribution network to shunt the condensate back using steam. We wouldn't need electrical energy at that point. But when it comes to removing the condensate from the distribution pipework, if we're distributing the steam at a nice high pressure, we're typically going to have more than enough energy in the steam to ensure that the condensate can be driven back to the boiler house for reuse.
Okay, excellent, lovely. Thank you. Very full and complete answer there. Thank you very much. And there's another question from Ruben. And he says, I know industry requirements can vary, but what is the recommended material for steam supply and condensate return when specifying pipes? So materials of construction for pipe work on both sides of the system.
Another good question, and I think I'll refer back to one of the very first slides that we went through. Depends on the process, depends on the application. For example, if you're in a food, beverage, pharmaceutical plant, then we're going to want to ensure that the steam distribution pipework is not only is it clean and dry, but we're going to want to ensure that we don't have any risk of corrosion, microbial growth. And we'd probably be distributing the steam in 316 stainless steel pipework. If we were just distributing the steam for general purpose, for heat transfer, for example, then typically we would be distributing it in carbon steel pipework, shed 40, shed 80, depends on the pressure. The pipework contractors and the consultants would typically take an opinion on that.
Okay, so again, varies with individual site and process conditions, obviously.
Pressures, temperatures, what it's is it what it's exposed to. It's a difficult question to answer, but typically shed 40 carbon steel.
Lots of variables to think about in there. Yeah. Okay. Excellent. Good. Another question. There's a couple of extras flying in here, so we'll keep you on the line while we've got you, if that's all right. So we've got a question from Daniel, and he says, "Good afternoon. We have a boiler operating at around 7.5 bar. I presume that's bar gauge, which is then reduced at a pressure reducing station to 5.6 bar for network distribution. Why is this done? Is this to do with latent heat, etc.?" So just a quick explanation again about pressure reduction there.
Yes, it'd be interesting to know where the pressure was reduced. Typically, we want to generate the steam and distribute the steam at the highest practical pressure. So we use the example of 10 bar gauge, for example. It could easily be 7.5, as you mentioned. And we want to distribute the steam at that pressure for a greater distance as we can. We want to get it as close to the process as we can. It helps us to ensure that the steam is kept as dry as possible. It helps us to ensure that the steam can be distributed in a small pipe diameter, but by stepping the pressure down as close to the process as we can, it helps us to ensure that we get the temperature we require at the process because of that pressure temperature requirement. But it means we're not distributing the steam in an unnecessarily oversized infrastructure that is not only going to be costly, but it does mean that it's far more likely that that steam would then degrade. What we wouldn't want to see is the steam being produced at 7.5 bar in the boiler house, and that pressure being let down, in the boiler house or very, very close to the boiler house, because that wouldn't necessarily be the best way to distribute that steam. Okay.
Yeah, lovely, good, very clear explanation again there. Thank you, Dan. Excellent. I'm going to hit you with a two-in-one question now. So this is a question brackets S from Mike. and he's asking, what are the best methods for measuring dryness fraction of steam? And what is a typical figure for percentage of condensate return to a boiler plant?
I'm going to answer the second question first there. What is a typical figure of condensate return? Well, again, depends on the process. If we've got a pharmaceutical plant that's got a lot of humidifications, a lot of plant rooms, then the condensate is lost in the atmosphere. The vast majority of the condensate isn't available to recover. Or we could have a factory that was operating with 100% closed loop system, closed loop heat exchangers, in which point then we would expect a significant condensate return level. As a very, very broad rule of thumb, we like to aim for somewhere between 80 and 85%. So if you're generating 10,000 kilograms per hour of steam, we want to see 8,000, 8,500 kilograms of condensate coming back to the boiler house. So next question typically is, well, how much am I bringing back? And the good news is that that can be calculated very, very easily using a ratio. And the good news is steam using sites, they will already be doing that on a daily basis as part of the HSE BGO1, BGO3 requirements. So if you spoke to the boilerman or the boiler operator, he'd be able to give you a percentage condensate return. If it was significantly less than 80%, then alarm bells should really be ringing, because there's a huge opportunity there to optimize the amount of condensate coming back and enjoy a significant cost saving. So with regards to the dryness value, it really depends upon what we want to know the dryness value for. For example, we could be using steam for direct injection purposes. For example, it could be for humidification of a hospital operating theatre, or it could well be that we're supplying that steam into a sterilizer of sorts. So typically, we'd want to measure the condition of the steam, and if we're working to BSEN 285 standards that benchmark the steam condition, we're going to want it to be 95% dry or better. But if we just want dry steam to ensure that we're protecting the infrastructure against erosion, corrosion, water hammer, steam with little energy in it, then we can typically achieve that by having an appropriately sized separator ahead of the process, ahead of capital equipment, and behind the boiler to strip out any entrained moisture. Measuring steam dryness, it is quite an art, and that is typically something that would be outsourced to a steam specialist, a third party such as ourselves or any other that would be able to provide the appropriately trained engineer on site to give you an understanding with regards to where your steam condition lie.
Okay, and possibly as part of some overall survey or audit, perhaps, of the system in its entirety, maybe as well. Dan, would that be true?
Absolutely, but again, it really comes down to understanding what the steam is being used for. Every process needs to be considered on its own merits, and what may be overkill in one industry would be fundamentally, it'd be critically important to another.
For sure. Okay, lovely, good. Thank you very much. Just a couple more very quickly, if we may. So there's a question here from Ali, which he's asking, can we install a plate heat exchanger horizontally when using steam as a heating medium?
No. We need to allow for the condensate to be able to drain away correctly. So typically, not a plate heat exchanger. You may be able to install a shell and tube heat exchanger horizontally, but with a plate heat exchanger, we want to see the steam being connected at the top of the heat exchanger, condensing, and then the liquid condensate can fall under gravity and be taken away to ensure that we keep the steam space as dry as we possibly can.
Yeah, Absolutely. And then, I've just noticed actually a little follow-up point from Mike here actually regarding the question about condensate return. This is so what he's followed up with an additional comment for us where he's saying we are pretty much a closed process, but only currently returning around 47%, which I would say is quite poor. We also have vent condensers on CRU vents, so just a general observation there about the current condensate return rate, which I think we would probably agree that that's fairly low, Dan.
It is low, and there's an excellent opportunity for you to enjoy a payback there. You'll probably find that you're consuming more water than you'd like, you're consuming more chemicals than you like, and of course you're burning more fuel than you'd like. 47%. Yeah, that's we need to identify why that is. And it could well be that you're condensing steam at processors at very high pressures and temperatures. Therefore, you've got quite a lot of flash steam being emitted or being lost. It could well be that you've got large steam traps that have been left failed in the open position for a prolonged period of time. Could well be that you've got leaking steam pipes, or you've got leaking pipe work somewhere, an underground culvert or something. But yes, 47% does sound on the low side.
Certainly sounds like a good opportunity for some improvements there.
Definitely. A good rule of thumb is, if you look at the temperature of your feed tank, if your feed tank is held at a temperature that's significantly less than 85 degrees, then alarm bells should be ringing. And we do know that feed tanks can be held at that temperature artificially as a result of direct steam injection, at which point all you're doing is taking steam from the boiler to elevate the feed tank temperature. So it's a cost of energy in order to do that. But if we can recover more and more condensate, we can elevate the temperature of the feed tank organically. And a 6-degree increase in temperature is typically going to result in a 1% fuel saving.
Okay.
So I'd encourage Mike to have a look at his feed tank temperature as well, and that's certainly something that one of our engineers will be able to assist with. And
absolutely,
if he'd like to contact me at any point, I can put him in contact with the people that can help him out with that.
For sure. Thank you. Excellent. All right, lovely. And hopefully, thank you very much, everyone, for all the good questions there. Some really good points raised, and hopefully we've been able to answer those completely for you.
Yes, thank you, Steve. Anything to add, Brian?
Other than to give a couple of closing remarks. So thanks for those fantastic questions. Thanks for great answers, Dan. Sounds like there's some opportunities for doing some good works there for some of the guys that have connected in. Thank you for Nikki and Fiona for their help putting the show on today. And as always, it's a big thank you to Dan and Stephen and Spirax Sarco UK, who do a great job giving these lectures completely free of charge to the Institute of Mechanical Engineers. And also a shout out for the Project Solutions team who support me and help me get these lectures out in the public domain. So thanks everybody. Really enjoyed today's lecture, and goodbye.